As a quick note regarding the previous result on MacBeath, I have here a family of triangles interscribed between a circle and the MacBeath ellipse. This is actually where that name stems from. The MacBeath ellipse for a triangle has foci on the circumcenter and on its isogonal conjugate, the orthocenter. And we know that the a midpoint of these two triangle centers is x5, which is the center of the caustic. But that's not germane to this discussion. What's germane is that, as I had mentioned before, and we had seen on the other tool, not only does this family conserve, as every other Poncelet MacBeath conserves the sum of side lengths squared and the sum of the double angle cosines, but specifically for n equals 3, we also get this additional conservation, which is the product of internal angle cosines. Notice that this is not conserved, for example, for n equals 4. It's not conserved for n equals 5, okay, this product over here. But it is conserved somehow for n equals 3. So I'm sure this is something that can be proved with analytic geometry, this conservation. Everything in n equals 3 becomes can be manipulated, right, with analytical geometry. But I want to introduce another experiment here, which was suggested by Professor Rich Schwartz, which is, well, since the side lengths squared are preserved, the sum is preserved, you got the equation of a sphere, right? So a sphere in Rn is the set of points where the sum of the square of the coordinates is conserved. So let's take the coordinates here being the side lengths themselves, and we know that over this family, the sum of their squares is preserved. So the side lengths should be on a sphere, and that's what I plotted here. Here's a sphere, and I'm basically taking Poncelet n equals 3 as you saw above, but for several values of the aspect ratio of the caustic, namely almost 1, then 1.1, 1.25, 1.5, and 2. And for each one of these curves, I'm plotting them as the black, red, green, blue, and orange curves. So you can see here that when the aspect ratio is 1, your curve is going to collapse to a point. And as you start increasing the aspect ratio, so you start increasing the aspect ratio of your caustic, your MacBeath caustic, okay, you end up getting something like that, right? And the curve that is being swept, the spherical curve that is being swept, is actually, there's a limit here, which is probably 3 great circles. And that's interesting in and of itself, right? So you can see here that the set of curves is actually tending, right, to probably what looks like 3 great circles when a over b of the caustic goes to infinity. So it'd be interesting to actually study the geometry of these curves, and Professor Schwartz had actually said what happens to these curves in R4, R5. Maybe R4 has some interesting geometry, because as we saw before, when n equals 4, you got this additional property that the sum of the side lengths squared was 8, right, for a unit radius outer conic. So maybe there's going to be some interesting geometry for R4, but then again, how do I visualize these higher dimensional spaces? Although we could perhaps do some studies with the curvature and whatnot. Okay, so that's what I have for now. See you on the next video.